Alright, hey folks, and welcome to Chapter 4. So, this is gonna be weird. We're just gonna deal with that fact. It's gonna be strange. Um, I've never done anything like this before. I don't think any of you have ever done anything like this before, but we're gonna get through it together, so let's do our best. So, we're gonna get started with Chapter 4. I'm gonna post videos like this. I'm gonna try to do one every day, so that way I know that some of you can't make it to the specific class time, so I'm gonna prioritize things like this so that whenever you can manage to go through the material and take your notes, you can do it then. So we're going to start with, this is my intro video for the chapter, so we're going to talk about a few things to get you started, and then I have the slides posted right here as well, so you can work through those. I'm not going to go through every slide with you with this video, but I am going to give you kind of an introduction, a setup, and then the next video I have on here is also kind of the wrap-up, which is going to summarize a lot of things and go over the main takeaways you need to know. So, right now we're working with constant ratios and right triangles, so we're dealing with trigonometry. We finally made it. Not the way I would have necessarily wanted to go through trig, but this is how we're going to do it. So we're going to get started with trigonometry. It's it's going to be a lot simpler, or it's not as complicated as you might think. So let's get started then.
All right, so we're going to start off with our warm-up here. So our warm-up is going to be reviewing what a slope triangle is and how we use it to calculate slope. So take a look at this example right here, this image. We've got a line. We want to figure out what its slope is. So if you remember, a slope triangle is a right triangle that we draw along the slope of a line so that we can figure out its slope. And if you remember, slope is always rise over run. And remember, we always got to check for a positive and negative slope. We worked with this a bit in Chapter 1 when it came to perpendicular lines, so we've worked with slope before. So go ahead and work on this problem. I'll give you a second to pause so you can work on it and then restart when you're done. So go ahead and pause now. Okay, so starting back up again, you should have gotten that, first of all, this is going to be a negative slope. We can tell because if we dropped a ball on top of this line, it would roll down to the right. So that tells us the slope is negative. Next, we want to figure out a rise over run. So remember, it's always rise over run, change in y over change in x. So if we just count, we can see that between 0, 5 and 3, 3, we go down 2. So our rise is 2, and then our run, change in x, is going to be 1, 2, 3 from 0 to 3. So that means our rise is 2, our run is 3, and remember it's a negative. We got to make sure we put that negative in there. So we're going to get a slope of negative 2/3. And we can just draw a line basically from 0, 5. We can draw a line down 2 and then draw a line over 3. And that right triangle that creates with the line segment between 0, 5 and 3, 3 forming the hypotenuse, that right triangle is our slope triangle. And that's what we're going to be working with today. So this is going to be helpful for you as you go through the lesson. Now we get into the first problem, which is the Leaning Tower of Pisa. So we've got the Leaning Tower of Pisa. It was built in the 1100s, and because it was built on a poor foundation, it ended up tilting to one side. So normally if something is built on a bad foundation, it'll sink straight down, but unfortunately the foundation underneath the Leaning Tower of Pisa was actually a little uneven. So one side was less structurally sound than the other, so instead of sinking straight down, one side is sinking faster than the other, so that causes it to tilt to one side, as you can see in the picture. So it's feared that if the angle of slant ever falls below 83 degrees, so basically 90 degrees is what we want, that'd be perpendicular to the ground, and as it tilts over, that angle gets less and less and less. So if it gets below 83 degrees, it'll collapse because, that'll get to the point where it's tipped over too far that it's just going to keep going. You know how, like, if you have a water bottle and you stand it straight up and down, if you tilt it a little bit over to the side, it'll right itself, but if you get to a certain point past that balance point, it'll just tip over. And that's what they're worried about. So engineers wanted to try and find out the angle that it's at, so they decided to drop a weight from the very top corner of it straight down and then measure the distance from that over to the base of the tower. Now, you might be wondering, like, why didn't they just measure the angle? Well, if we think about it, this is a nearly 1,000-year-old tower, 900-year-old tower, that is made of very, very rough stone, and that stone is sinking into the ground, which is not going to be even. So if we imagine the angle of that creates, we've got really rough stone intersecting with very lumpy dirt. It's going to be really hard to get a precise angle there. That could give us anything between like 60 to 120 degrees. One of those wouldn't even make sense. So because it doesn't create nice crisp lines that intersect to create that angle, we need to come up with some other way of measuring the angle that's not just measuring it directly, because it's just not going to happen. If you imagine going outside and trying to, look at the angle of a tree growing out of the ground, well, the ground slopes up. It's not exactly flat and even. It's just not going to work. We're going to need another way, and that's what we're looking at here. So these are the 3 questions we're asking. With the measurements provided above, what can you determine? So looking at this diagram, what are some things we can determine? And if the answer is not a lot, that's okay, but just use the tools we have to see whatever you can calculate. Just throw every tool we've got at it, see how much you can calculate with this. If it's only one thing, if it's only like the length of the hypotenuse, that's okay. That's what we can do. Part B asks, can you determine the angle at which the tower leans? Why or why not? So this is the information given. You can't use a protractor. You can't just like hold a protractor up to the screen and try and measure it. It's not going to be accurate. Remember, we don't trust the picture. We trust the numbers. And so basically just could you or could you not? If the answer is no, that's okay. Just why not? And then it says at the end of this section, you will know how to find the angle for the situation and many others. So we will actually, no matter what your answer was to part B, you will be able to, by the end of this section, solve for that angle. But for now, is there a way we can describe the lean of this tower? Is there a way we can describe how far over it's tipping? I'll let you pause here and work on that, and then restart again when you're ready for me to go over some of the answers. So pause here. Okay, so I'm going to go through these now. So for A, with the measurements provided, what can we determine? The answer is kind of not a lot. The length of the hypotenuse is the main thing we can figure out just by using the Pythagorean theorem with 5 squared plus 50 squared. But that's also necessarily not that useful in this situation. So we don't have a lot that we can really figure out given the tools that we have. For part B, we actually can't at this point. With the information we've learned and what we know and the tools we have, we cannot determine the angle that this tower is leaning. So basically, because we have no way of connecting side lengths and angle, we've kind of connected them through similarity, but we don't have a triangle this is similar to with its angles written in to figure that out. So if for part C, if we wanted to figure out a way to describe the lean of this tower, how far over it is leaning, well, the best we've got is, if you think back to the warm-up, slope. We can figure out the slope of this line, how much it's leaning. So if we do that, well, if we look at rise over run, we've got a rise of 50 and a run of 5. We discover that we've got, 50 over 5. Well, that simplifies to 10. So we have a slope of 10. So what this is going to come down to is that this entire chapter is focusing on the fact that slope and angle are 2 different measurements that both describe the same thing, how far over something is leaning, how slanty it is. So there must be some connection there. There must be some way to take this slope that we have and turn it into angle, almost like a conversion factor. If you think about it, they're almost like 2 different units describing the same thing. It's almost like feet and meters. We can convert from feet to meters and meters to feet. So there must be some way to convert from slope to angle and angle to slope, and that's what we're going to be working on. So here is where I'm going to leave you, basically. This is the part where I'm going to stop going through the questions and we'll let you go through them on your own. I have another video posted here that's going to kind of summarize the takeaway. It'll go over the last couple of questions and then summarize your main things to take away from this section. So work through these. If you have any questions about anything specifically, let me know. I'll be available. So I'm going to leave you with the second problem here, which basically this is on this is one of your first resource pages. If you have access to a printer and you can print your resource packet, go right ahead and do that, and you can work through these. Otherwise, you can just graph the following line on a piece of graph paper. You see it as a slope of 1/5. So for every 1 it goes up, it goes over 5. And it mentions here that it has an 11-degree angle. So for the rest of this chapter, we are going to kind of round our angles for this, because a slope of 1/5 does not have an 11-degree angle exactly. It's very, very, very close. Something like 10.8, I think. But the important thing is we want to just investigate the relationship between slope and angle. So for right now, we're going to use whole numbers for both of them with the acknowledgement that we are really heavily rounding here. So this 11 degrees will work for now, and we're going to use it, and it's going to be really useful in investigating and describing these things, but it's not necessarily exactly accurate. So take a look at this. So either print out the resource packet and have it and be able to use it, or just graph this on a piece of paper and investigate the questions on the following slides using this. So when it says later to graph additional slope triangles, so this is a slope triangle right here, when it says to graph additional ones, start from the same point. It'll really make the problems easier if you start from the same point on the left where this one is starting and kind of extend them over so they all share that 11-degree angle, as opposed to like starting them further down to the right. All right, So, again, if you have any questions, let me know. You can get in contact with me, and I will be happy to help you out. If you need me to, I will hop on to Google Meet, and I can talk to you about these in person. And check out my next video for a summary of this section and kind of the main takeaways that we should be getting from this. All right, so good luck, and I hope this goes well for you.